I'm Jeff Rosenfeld with BAMS, and I am here with the 2013 recipient of the AMS Award for Outstanding Achievement in Biometeorology. And this is Thomas Foken, and Thomas is with the University of Bayreuth. And Thomas, congratulations.
Thank you
very much. It's a wonderful honor. And I understand that you're a professor of micrometeorology.
Yes.
Maybe you could explain what that is for those who don't know.
Oh, micrometeorology is the physics and partly also the chemistry of the atmosphere in smaller scales. In smaller scales, this means in the boundary layer, the lowest kilometer of the atmosphere, and in a horizontal distance, we speak about some kilometers, up to 20 kilometers. So it is, for most who know the meteorological scales, it's the meso gamma scale and lower scales. And this is the area where the people live. This is the area where we have the interaction with the biosphere and the atmosphere, to the soil and to the water. All what happens near the ground happens in the area of micrometeorology. And so all the parameterizations in the global models which touch these scales have parameterizations which micrometeorologists investigate.
So there's an interaction with biometeorology, but micrometeorology isn't exactly the same as biometeorology.
It is not really the same. We must say micrometeorologist comes from the direction of the meteorology to this problem, and has to learn a lot of the plants, of the soil, and so on. And others come from the other side, as they are biologists. So maybe the Fluxnet community is a community which combines meteorologists and people who work in biology and soil science and so on. And so biometeorology is an interdisciplinary science and brings a lot of scientists together. And we are happy in Bayreuth. We have courses where we investigate plants, where we look in the soil and in the atmosphere. And so we teach students in all these different sciences. So they are ideal for biometeorology, or for nowadays we often say biogeosciences is a more popular term.
Just to make it more complicated.
Just to make it more complicated, and so we have also more the soil included, and more the chemistry included, and so on.
Now, you got your start already with a sort of interchange of sorts. My understanding is your first research was basically in areas where the ocean and land were meeting. In other words, coastal issues, right?
Yes, I started at the coast. What is today called air-sea interaction, and my basis is a little bit a Russian basis. So my advisor of the PhD was Professor Kitagorsky, a famous professor in ocean science and the atmospheric science. My teachers were Professor Obuchov and Professor Yaglon and Professor Zwang. So I have a large background from Russia, and with Obuchov and Zwang I came into the field of air-land interaction. So my first experiments in Russia were on the Caspian Sea, and then my experimental sites changed to the Volga steppe region, comparable to Kansas steppe region. Mm-hmm. And there I started with the Obuchov theory and all these things, what was done at this time. So I'm really about 40 years in this job now.
So the connection with Russia is that at the time you were in Berlin, in East Berlin, is that correct?
I was in East Germany.
East Germany.
I was in East Germany, studied in East Berlin, and made my PhD in Leipzig, and was a lot of times in Moscow and in different places in Russia.
Now, what were the main research interests for you at that time? I understand that the coastal and air-sea interaction question. But what were you mentioned Obukov, and maybe you can explain a little bit about where this fits into the work you were doing, with turbulence and boundary layer issues, perhaps.
Yes, for me, the air sea and the air land interaction is not really different. It is only a problem of, on one side you have waves, on the other side you have plants, also with a high roughness. It's nearly all the same. And we have more practical issues over land. So I came to the land, and you know the biosphere is a very important part. And when we look about the climate problem, you know the biosphere is often a sink of carbon dioxide, but we do not know how effective is the sink. And in some years it's a source, in other years it's a sink, and this process is difficult. And we have in canopies, and this is a very interesting part for me, maybe especially the forest where I'm working very much. These canopies are so complicated in turbulence. And for me, always was interested the limits of all the theories. So the Obukov similarity theory doesn't really work in a forest canopy, but there are other processes. And we have a turbulent mixing which is suddenly very strong, and then it stops, and there's nothing changed, and all the gases emitted from the ground and the soil are collected in the steam area, and nothing happens, but there's a big chemical reactor. Suddenly the chemical reaction times are shorter than the transport times, and this is, I think, the big challenge which we have now when we combine biology, the effect of the plants on the process, together with the chemistry and the micrometeorology. And always when we do this, we are able to understand problems better, and we can look in the literature, and often we see, okay, they have made a good job in biology or in chemistry, but they did not understand the transport problem, and the transport problem is a very fast problem, sometimes a very, very fast problem. And there comes a breaking gravity waves through the atmosphere, and suddenly everything changes.
The different scales interaction.
The different scales interaction, yeah. It's a very specific problem, and it's also a problem of understanding of the communities. Each community comes from a different thinking in the scales, yes? And the plants all is very slowly, or the soil extremely slowly, and the atmosphere extremely fast, and it's not easy to bring this together, not easy to parameterize the process in the right way, or to find measuring techniques which are appropriate for all the different parts of the environment. And this is really a quite interesting thing, and there's a lot to do with also in the future.
Well, I want to ask you a little bit, before we get to the future, one of the things you talked about is how different processes come along and introduce a new complexity to the question of where the energy goes, for instance. It's sort of leading up to this question of the energy balance. Yeah. And why is that important? The closure, because you've been working a lot on that issue.
That is I have some problems which are follow me the whole life. So the first time the energy balance closure it's not closed, I found exactly 30 years ago, but it was impossible to publish this. So reviewer said, oh, you have to calibrate your devices and you will find that all is okay. But now it is well accepted, and the problem is now which part of the energy balance equation is not closed. Is this a distribution to all the parts? And with the help of large eddy simulation, we now know that circulation patterns are important for this closure problem. This is also a great benefit of the last year, that large eddy simulations work very well, and we can do a lot with this of the computer side. So energy balance closure is a big problem because I think it is not known to everybody. Everybody uses data from eddy covariance data and doesn't know that these data are, I will not say wrong, but there are some problems in the data. and you have to take these problems into account. And perhaps the good news is that we agreed in a workshop, many scientists all over the world, that this probably doesn't affect so much fluxes like carbon flux, so we have not to revise all the flux data. But nevertheless, when I was today in the hydrology community, the evaporation must think about this problem a little bit deeper. Yeah? And so it is still a problem which must be addressed to modelers, to all the users of eddy-covariance data, to know the problem, to think about the problem, and to learn a little bit about this. And this is one of my life to work on this energy balance closure.
It seems like a fascinating problem that keeps getting more complicated, from initially thinking it was simply a data error to all sorts of, or measurement error, to all sorts of factors.
It was first a measuring error. We looked into devices. We have done lots with the devices. We looked into soil. If the soil does something, we looked into storage in the plants. So you see that it's biometeorology is the problem. Yeah? And suddenly comes some problems in the boundary layer. In the whole boundary layer process we have to understand, and it makes everything so complex. Yes?
So you have to pull in teams of people from all different departments and disciplines to solve this.
I have in Bayreuth different departments who we cooperate a lot, but I have a very well cooperation, I think, all over the world. Yes? So I have good friends in Boulder, and I have colleagues in Australia and somewhere else, and we have a lot of papers together, and this is it's the only chance to do such things, that these people come together also to bring the energy balance closure problem, to make it public. So we had a meeting, now it's 20 years ago, and it was in Grenoble. So people like Larry Mart and Steve Angley, and we came all together and discussed this problem, addressed this problem. And suddenly it was possible to publish something in this field, which was before not possible.
It's very hard to publish if not everybody thinks it's real. Now, I do want to ask, transport is a big part of studying the boundary layer. And speaking of transport, I understand that you know a little something about model trains and study of the canopy using train in your research at Bayreuth. Can you explain? I see you moving. What is this about your instrumental setup in the forest there?
Yes, I'm coming from the experimental side, and so I thought all my years about the typical instruments to do something. So the idea of such a train is not absolutely new. You have heard perhaps from Steve Angley that he has a tramp in the forest.
A tramp. Okay.
And this was a hanging tramp, and this was a train. We had in a height of 1 meter in railway system, a small railway system, and this railway moved 75 meters into the forest and 75 meters out of the forest. And the main problem is how interacts the forest with the clearing, and how we see this in the data. We had a lot of towers and a lot of colleagues coming also from US and take part in this experiment. And the main idea is what happens at the forest edge. Which structures are there, and heavy current structures at the forest edge, and heavy sweeps or ejections there. And we investigated this with turbulence instruments. The first paper is now accepted in boundary layer metrology about it. And with this train, we looked how the mean parameters are changing over this long distance. How is the infiltration of air from the clearing into the forest or out of the forest. And the most interesting thing is that we do not use only meteorological parameters, we use also ozone as a tracer. It's a very nice tracer. And so all this combination, this atmospheric chemistry is quite interesting to understand some problems. Often the moisture or temperature is not the best parameter to look in such things. Sometimes a tracer like ozone or nitrogen oxide or monoxide are also tracers to see something what happens there.
So the train carries the probes, the instruments back and forth.
Yeah, yes, and every 5 minutes it came to the same place, and we have a day record of all these things.
It sounds a lot more fun than just hanging balloons in the air.
Yes, you must have also some fun in your science.
Well, what would you say has been the thing that has brought you the most fun in your career in terms of your science?
I have done a lot of things.
A lot of things that you would admit, that you would tell us.
My PhD thesis was a drop zone falling into this ocean and measures the temperature structures in the first centimeter air above the ocean. And I created a model from this, and this is still now working. Fun is also, I was in Antarctica, and this was not fun to go to Antarctica. There was a reason to investigate stable stratification. Stable stratification in the atmosphere is extremely important, and you can investigate stable stratification under European conditions 1 hour every second day very well. So then you must go to a place where you can do this. And so I made some measurements in Antarctica. Also 20 years ago, but the data we still use, and more interesting, I measured inside an astronomical telescope the turbulence.
Inside the telescope?
Inside the telescope and outside the telescope to look where the scintillation of the light of the stars is an important factor for astronomy.
Yeah.
And a big part of this scintillation comes from inside the telescope. Yes? So you have to look that there is a good mixing inside the telescope, and such things always to work in the field of atmosphere ground interaction, and sometimes do some things where your knowledge is good to do other things. This makes fun, I think.
Yeah. So what's next then?
The next is that I will retire in 1.5 years, and I hope for that a new professor comes to Bayreuth and continues his work, and I will write. I have a textbook on micrometeorology, and I'm working on the next edition, and so I will do something to bring my knowledge on paper that my students can learn, and that make some textbooks and such things. This is the aim of the next time, and I have a lot of PhD students in the moment, approximately 10 who have no.
You can't retire.
So you must finish in the next year.
Yeah.
So this is also a big job, and the great thing is that I like very much to teach, and when you teach and you have students, master, PhD students, and postdoc, then you know that you bring your ideas to the large community. It is much better than to write only papers which are forgotten in Google after 2 years.
Right. Yeah.
And this makes also a good connection to US, and of my group, 2 are professors in the United States already in biometeorology. And I think this is the best thing what I have done, not also the measurements, but to teach a lot of students, and they use ideas they got from me, and they develop these ideas. This is a good thing.
I think that's good you mentioned that, because the citation for the award not only mentions your contributions to the understanding of these processes, but also to the measurement of these processes and the observation of these processes, and also the educational aspects that you brought to your career. So I want to thank you again for your award and or for talking to us and congratulate you on this award.
Thank you very much. It was a pleasure for me.